it needs more than it has. So this is what happens here. And the row axis, you can see it progresses much more easily. So it can store all addresses using only one register. So it's only a multiple of that address. This is the same as before, but for as larger matrix. This is a matrix 32. The main difference between both is the first one is unrolled. This one is not unrolled, mostly because the processor doesn't have enough registers to try and unroll it. So you can see the first 3 lines. This is the innermost loop. You can see that for the innermost loop, you do have one extra access for the column with those lines and brackets. Those correspond to a memory access. So you can see from one code to the other, and column access, you have one extra in the innermost loop, and that is the costly, the higher cost loop in the program. So if you do one extra access, you're going to have in the end a lot more access than the raw version. So this was the very first optimization we did, just changing how we're accessing the data. And then I mentioned the load imbalance. For this, I brought the algorithm. It's really quickly. In our parallel implementations, our parallel region starts at line 6 with this loop 4K. And what it does, this loop reduces over time as we take different matrices. This loop is going to reduce its limit. L is going to go from a very large number all the way to 1, while the inner loop, the loop in line 7, is going to get bigger and bigger, and that is what causes the load imbalance in this problem. So what I did, I took an if statement that whenever L is smaller than the number of processes I'm using, we instead change our parallel region from line 6 to line 7, and that mostly fixes the load imbalance problem. As you can see in this table here, this shows our parallel implementation and from the original code, and then from the optimized, you can see even for smaller matrices, you can see the load imbalance, but for larger ones, it's very expressive. And the optimized version can fix it. And for the second, you can see how the speed up also greatly increases in this case. We do have a much better speed up that shows a lot more what we expected to be, roughly 3, like it was for the other cases. So finally, this is our last attempt at optimization. We did a vectorization using Intel SSE, which limits our vectors to only be 4, because SSE is a fairly older technology, and it limits us to 128 bytes variables. So we're limited here to 4, all of our data as floats instead of doubles, so I could at least see 4 here. So you can see in our table how there is a not significant but interesting speed up even for a very small vector size. As the matrix get larger, we do have an increase, a better increase for matrices of size 20, 24, 36. They're also interesting, around 2.8 as well. So even for a fairly old technology, we could still see an interesting result. So this, as a conclusion, there are 3 possible optimizations identified in our analysis. That they would work on both execution time and the memory, we can conclude that correctly. Choosing the data access pattern for this problem is very important. A possible future work here is taking CSR matrix in consideration for both the data access and for taking different matrices in account. The loading balance in this problem is very expressive, especially for larger matrices, and fixing it brought a very good result. And finally, the effective optimization with it's possible to even optimize with a fairly old processor and give a good result, which is both interesting and gives a good light to this problem. I'd like to thank you all for watching. And that's it. I'll see you in the Q&A in a few minutes.
Okay, thank you very much, Alexandre. Anyone has any question for him? If you want to put on a chat, if you want to turn on your mic, you can turn on and make the question live. Well, meanwhile, I have one question, Alexandre. Did you consider sparse matrix in your computations?
No, not yet. They are all full matrices as of right now. This is the next step. One of the ideas right now is to take the CSR. It's a way of understanding and of implementing the matrix inside the code, where we take sparse matrix much easier into account. So this is one of the ideas right now, is to take this representation, the CSR, to try and bring the sparse matrix into this algorithm.
Okay, and do you think with sparse matrix, the computation will be different and your results will be different?
For this matrix, yes, I expect them to be different because everything is different. When I take this new representation, which is the CSR, the dot product is going to change. So the data access pattern is going to change too. So I expect different results from this.
But I just want to make a remark, because when you use vectorization, SSC, or AVX, you have to take care of data alignment.
Yeah.
So when you are using sparse matrices, for sure you compress the memory, but the problem is that you can suffer from misalignment. So this has to be managed carefully, because in your implementation, I guess that you didn't manage the alignment cases. You just leave it to the compiler.
Yeah, you can align. The compiler aligns for itself.
Yeah.
There's the bright side about this CSR, Claude, because all of the data is stored in a single vector. So it should be alignable by the compiler, because it's not going to be spread around the table. Instead, it's going to be just one vector, and we're going to access it in. I mean, vectorization in this case is probably going to be complicated, because because the matrix is not the problem here. It's how we're going to multiply by the vector, because the CSR in this case, it's only a vector. I can align this vector, no problem, but it's not going to fit with the rest of with the other vector I have to multiply. I have to look at it. Should be easier than doing a full table, a full matrix, than trying to multiply by a full matrix.
Okay, it's nice that you are aware of that.
Okay, thank you very much, Alexandre. Nice presentation and nice discussions. So let's go for the second presentation, which is towards a pervasive containerization of HPC job schedulers. This presentation is recorded, and after the presentation, we can have some questions with the authors. The authors are here?
Yep, hello.
Nicolas.
Okay, okay, good.
I'm Nicolas.
So, okay, in the end, we go for questions.
Okay.
So, Danielle, can you play the presentation?
My name is Nicolas Greneche. I'm PhD student at University Sorbonne Paris Nord under the direction of Professor Christophe Serrin. Our paper is called Towards Pervasive Containerization of HPC Job Schedulers. Our work is to enable cohabitation between HPC jobs and more regular containers such as databases or web servers. And all this stuff must run on top of a regular, that's to say unmodified, orchestrator. The presentation will start with results of a survey launched on several HPC centers to determine if our work is of interest or not. Then we will make a very, very brief reminder of how HPC schedulers work. Then we will continue with the main part of our paper, our containerization proposal. This proposal will be followed by a performance evaluation. The main motivation of our survey is to evaluate the overall waste of cores. We conduct this survey on 12 HPC clusters of various scales. The first one is what we called local scale. This is typically the cluster you can find in your university. The second one is the national scale. These clusters are more powerful, but they have more drastic access rules. You may need to prove that your code scales on a local cluster before any access. The last one concerns specialized cluster. This kind of cluster is tailored for one given usage. The result of this survey is a scatter plot. It aims at evaluating the bad impact of a given job on the whole set of jobs. We calculate the ratio of time wasted by a job on the sum of whole time of all jobs. Y-axis is the efficiency of the job, that's to say CPU time over elapsed time. And the x-axis is the calculated bad impact. Jobs located on the upper left are efficient and do not waste time. By contrary, jobs on the lower right do not consume CPUs and waste a lot of time, maybe doing large I/O or doing nothing. This is typically the case of administration jobs that administration teams of each cluster run to check if everything is okay. Those are real values calculated over 6 months of logs supplied by administration teams of each cluster. As we can see, there is some wasted CPU time we could use for cohabitation with other kind of job. This diapo is a brief reminder of how HPC schedulers work. An HPC scheduler is made of a brain and several workers, also called computing nodes. The brain knows the physical resources topology and dispatch jobs regarding their availability. So, the user submits its job to the job scheduler. Then, this job scheduler selects a node regarding resources availability. If there are no nodes available, the job is obviously queued. The selected node, or set of nodes, launches the job. This is the step where containerization occurs in current HPC infrastructure. The job can be run in a container to perform file system isolation. This isolation supplies a self-contained image. The aim of this isolation is to ease dependencies management. Despite the fact that the image is supplied by user, it is considered secure because the container is setuided to user ID before instantiation. I don't really know if setuided verb does exist. The containerization can also be used for resources consumption control through cgroups. Finally, the job ends and exits releasing resources. The main asset of an HPC cluster is a very fine-grained scheduling. You can implement various paradigms of scheduling with a large set of entry variables to the algorithm. The drawback of this efficiency is that the hardware infrastructure is dedicated to HPC because the scheduler requires an exclusive access to resources. Our approach is to use an orchestrator to treat the HPC scheduler as a regular container. Basically, a container is a process that can access to a limited subset of resources. As stated in previous slide, the job scheduler is a process that forks the user's job on computing nodes, so it can theoretically be containerized. We can motivate this approach with two use cases. The first one is a user that wants to test his code on HPC scheduler with 6 cores and 2 nodes. In our approach, it means that 3 containers are spawned, 1 for the brain and 2 for computing nodes. The brain is told to use 1 CPU, the computing nodes use 6 CPUs each. After a successful run, the user ensures that his job runs with the HPC scheduler, and also that communications between processes are okay. This use case is quite volatile, and the job scheduler can be considered as a kind of launcher. The second use case is an organization that wishes to have an HPC infrastructure with non-dedicated hardware. This organization can instantiate persistently a multi-user HPC cluster upon an orchestrator. In our experimentation, we used Kubernetes orchestrator, Cryo container engine, and Slurm as the HPC scheduler. We instantiate several topologies containerized computing nodes, and we run HPCG on each topologies, mixing both MPI and OpenMP communication. We then compared results to a non-containerized Slurm. Results are supplied in the next slide. We can sum up and discuss the pros and cons of cohabitation. The first pro is that this approach makes sense with the cloud and the underlying highly converged physical infrastructure. Such a mutualization improves resources usage. The second pro is that it provides the sandbox environment for debugging to users. Moreover, system administrators, like me, can make a set of this sandboxing to deploy and test several versions of the HPC scheduler on the real, final physical infrastructure. The two cons are bound to each other. The use of cgroup as the resources isolation subsystem hides the physical CPU topology to the HPC scheduler. We had to develop a patch for all versions of Slurm to enable him to translate cgroup limitations into a CPU count. Our approach results in a kind of two-stages scheduler. This lowers granularity of HPC schedulers. Very first performances evaluation shows a very light decrease as soon as containerization is involved. you can see results in the lower right table. The first column is the number of containers. The second one is the number of MPI process. The third one is the number of OpenMP thread. The fourth one is the result of MPI communication bandwidth. And the last one is the CPU efficiency in teraflop. As stated before, we can see a very light performance decrease on the last column between the first line, which is a non-containerized Slurm, and the second line, a containerized Slurm. After that, performance remained stable. Now we can jump to the conclusion. As we saw in previous slides, our approach runs on a regular cloud infrastructure with a very little impact on performance. It is also flexible for not-so-HPC jobs. By not-so-HPC, we mean that not every user needs sharp scheduling for their job. In our survey, we saw that many users only specify a number of CPUs for their job. They do not use advanced features such as CPU affinity and the like. Roughly speaking, they need something faster and more persistent than their laptop. Moreover, with the growth of HPC users, there is a population that sometimes want to use an interactive instance of software for rapid test. And when it's ready, they run it at large scale on HPC cluster. With our cohabitation approach, they can do it. At this time of the presentation, it is very important to state one thing. Our approach does not aim at installing orchestrators everywhere in place of classic HPC infrastructure. Our approach is complementary to classic HPC infrastructures. Indeed, they could mix up to hybrid architecture where a queue of a classic HPC cluster can redirect to a set of containerized workers. These containerized workers trade a bit of scheduling granularity for elasticity. This is just another use, not a replacement. That's very important to state this. We will end this presentation with future works. First, we will study the new cloud-related features of Slurm to build a proof of concept. This POC will investigate the possibility of building elastic HPC cluster by combining our approach with the autoscale feature of orchestrators. We also have to perform a comprehensive study on performance evaluation. This work also includes security aspects. In HPC clusters, users can run their own image. In containers terminology, these images are called untrust images. Fortunately, Containers Engine can now use secure runtimes such as Kata containers or gvisor to add another layer of isolation to containers. We must quantify the cost of such an additional security layer. Finally, we can propose our architecture to other research teams to check if our methodology fits their needs. Machine learning jobs that require vast computing resources and storage are good candidates. So, this is the end of the presentation. Thank you for your attention, and it's now question time.
Thank you very much, Nicolas. Anyone has any question for him? You can open the mic.
Yes, I have one.
Okay.
Nicolas, you consider only the static scheduling of containers, right? Like a job scheduler. You don't consider the possibility of migration of containers among among the processors of a cluster. Do you consider, or do you intend to consider it?
We will attempt to consider it, but for the moment, our architecture is too small to make this kind of test. And we had to check if everything worked, because it seems to be easy to containerize a job scheduler, but there is a lot of things to do to make it operate smoothly. And now it's okay. And as I said in future works, we have to perform a larger benchmark, including security, but also including migration and checkpointing of workers.
I have a question. Can I?
Okay. Yeah, go ahead.
Hi, Nicola. Thank you very much for your talk. I am dividing myself here in two different talks, so I'm a bit confused. But I just wanted to ask you something. You mentioned at the end that you want to do containerization for machine learning applications. Are you acquainted with the Google Cloud Platform containers? Because I think Google has a containerized version of their AI package or something like that, where they do already something related to containerization. So I don't know if you know about that, or if this is related with the scheduling.
Yeah, I don't know about this because I'm not a machine learning expert. So that's why I want to get in touch with people that are very expert in this domain in our laboratory. And but I can guess that Google delivers a container of this application, and we have to open this container, add the HPC scheduling worker inside. We close the container and we run it. We will run it on our architecture, and I think that it will enable our infrastructure to schedule the Google container without any heavy modification.
Okay, thank you.
Any more questions?
I just have one question about the proof of concept. Okay. How do you plan to check that everything is working perfectly? I mean, checking the results, okay.
We will try two things. First, on this paper, we run HPCG for benchmarking, but I think it's a good one to see if performance are okay between the uncontainerized HPC scheduler and the containerized HPC scheduler. But to check if it's really okay, we're gonna get in touch with people that make machine learning at LEPN to check their work. And I will also see with people from mechanics and physics that already sent me code to test, donc real world codes, to check if there is a loss of performance. Because what is very convenient to me is that I run the HPC infrastructure in University Sorbonne Paris North. So I have access to this cluster, and that's people that already use this cluster with their code, and they do know well how the machine works and the performance with their codes. I can work with them to test my approach, to check if they can see differences in terms of performance results between the uncontainerized and the containerized experimentation.
Okay, so you will check with those people who sent you the codes to see if they agree. Okay.
I'm working on this code containerization for the moment.
Okay, thank you.
Thank you very much, all. We need to go to the next presentation. Thank you, Nikolai. Very nice presentation, good discussions. let's go to the third presentation that will be highly efficient Sgm implementation using DMA on the Intel Movidius Myriad 2. So the author is here.
Yes, I'm here. Hello.
Okay, so let's play your presentation and then we have 5 minutes for questions.
Sure. I am Suyash Bakshi, PhD student at University of Houston, and today I will be talking about our work, a highly efficient Sgm implementation using DMA on the Intel Movidius Myriad 2. This work was carried out by me under the guidance of my advisor, Dr. Leonard Johnson. Gem is a BLAST3 subroutine commonly used in scientific computing and many other applications. The conventional matrix multiplication performs 2n cube arithmetic operations over 3n square data elements. As such, the main challenge is to exploit the potential arithmetic intensity of 2n over 3. Such high arithmetic intensity makes it compute intensive, and an efficient compute kernel is imperative to achieve high efficiency. Moreover, it is also important to design a memory access schedule that can efficiently utilize all the levels of memory hierarchy to achieve high data reuse and minimize low-level memory accesses. As such, in this work we show that high energy efficiency can be achieved by efficiently scheduling compute and memory accesses together for an application like Sgem. Let us now take a look at the architecture of Myriad 2 chip. Myriad 2 is a 28 nanometer based SoC capable of running at 600 MHz and has a TDP of 1.2 watts. It contains 2 Leon cores, Leon OS in the CSS domain and Leon RT in the MSS domain. Myriad 2 also has 12 SIMD based specialized shave cores which are controlled by the Leon OS. Each has 3 arithmetic units, vector, scalar and integer, along with vector and integer register files. Shaves are accompanied by 2 MB Cmx memory, which is divided into 16 slices, out of which 12 are tied to each shave, who have direct load and store ports to them. The chip also contains a 512 MB LPDDR3 DRAM memory. Myriad 2 contains a direct memory access engine, which is a multi-agent, multi-channel engine, with each channel managing its own linked list of transactions. It allows to schedule inter-memory as well as intra-memory data transfers. As mentioned, the DMA operates using linked list of transaction descriptors, with each descriptor describing a single data transfer from source address to a destination address. By the use of linked list, multiple such transactions can be chained together, thus reducing the scheduling overhead. As a result, completion of one transaction in the list can trigger initiation of the next transaction. The DMA also supports 1D, 2D, and 3D transactions. Let us now take a look at our Sjm implementation. It contains 2 parts, the compute kernel and the data movement. These two are then efficiently scheduled together to achieve high performance and energy efficiency. Before we move to the implementation, here's a quick illustration of inner product, also called the dot product, and outer product, also called the cross product. These will be frequently used in the further discussion. Our Sjm Compute Kernel is similar to the kernel implemented for Myriad 1, which was published in IEEE Micro, for which the code was shared with us. However, we added optimizations to it that resulted in a 2% overall performance improvement, which is discussed later on. The compute kernel is a multi-level kernel with each level corresponding to the levels of memory hierarchy. We'll discuss them in a top-down manner, starting from register level, the Cmx slice level, and the Cmx level. The figure on the right shows mapping of unique blocks of matrices in the DRAM to each shave's Cmx slice. The innermost level kernel is the register level kernel, which is similar to the kernel for Myriad 1. It computes a 4x4 C block using inner product multiplication of 4x4 A and B blocks. The block dimensions of 4 is chosen based on the shave's vector instruction width and due to limited availability of registers. The kernel takes 19 clock cycles to compute 128 arithmetic operations, which is the minimum possible with shave instructions at architecture. This results in a throughput of 6.74 flops per cycle per shave. The next level is the Cmx slice level kernel, which is again similar to Myriad 1 kernel. Here each shave operates on its own local Cmx slice blocks of shape m' by k' for A, k' by n' for B, and as a result a C block of shape m' by n' is computed per shave. This is done using a block inner product traversal over A and B blocks of size 4x4, on which the register level kernel is then applied. Notice here that the storing of C block back to CMX is not overlapped due to limited register availability, which adds an extra 19 clock cycle overhead penalty per block inner product. As a result, a large K' is better to avoid the said penalty and achieve higher compute efficiency. As can be seen in the figure, the block inner product is first carried out for a row block of A and a column block of B. This is continued while moving across column blocks of B until all n' over 4 column blocks of B have been traversed, after which we move to a new row block of A. The next level is the Cmx level kernel. It is adapted from Myriad 1, but with an optimized calling method that results in a 2% overall performance improvement. At Cmx level kernel, each shave initially operates on their local buffers, as can be seen in the figure. Here we can see the first iteration of Cmx level kernel in more detail. As shown, each shave performs the slice level kernel on their local buffers. In the next iteration, all shaves access B block in the next shaves buffer and apply the slice level kernel on local A and C buffers, but with other shaves B buffer. Accessing of other shaves B buffer is carried out in a round-robin fashion and has similar access latency as the local slice. This is continued until all shaves have accessed every other shaves B buffer. In Myriad 1 implementation, shaves were halted to provide CMX addresses of other shaves B buffer. We alleviated this overhead by using assembly instructions and predefined offset to calculate the addresses, which resulted in a 2% overall performance improvement. As a result, the Cmx level kernel computes a m' times n shaves by n' times n shaves block of C. So that was about the compute part. Now moving on to the second part, which deals with data movement between main memory and the Cmx memory. For matrix multiplication, the two most common block traversal schemes are inner product and outer product based traversals. Here we see two versions of an inner product block traversal. On top, the naive inner product version, where blocks of C are computed row-wise by traversing A block rows and B block columns. To reduce the memory accesses, a simple optimization that can be applied is by reusing the last horizontal blocks of A for the next block inner product. As a result, A block rows are accessed in an alternating manner. Similarly, the last block of B, such as blocks 0, 3 in the figure, can also be reused. Unlike inner product, the outer product traversal computes C in a column-wise manner. Here, A is traversed across block columns and B is traversed across block rows. Similar to inner product, we can apply an optimization to naive outer product as well by reusing the last vertical A blocks and accessing them in an alternating manner. Also, the last block of C, such as block 0, 3 in the figure, can also be reused, resulting in comparatively lower memory accesses than the naive traversal. We now compare the data transfer requirements and the time required by both block traversal schemes. The graphs show data transfer times for different matrix sizes as a function of block dimensions for optimized inner and outer product traversals. We also show the total compute time for each case. As we can see, the optimized inner product yields lower data movement time for K' smaller than 300, and the outer product yields lower time for K' values larger than 400. Moreover, recall from slice level kernel discussion that a larger K' is better for compute efficiency, which is evident in the shown plots. Most importantly, the compute time always dominates the data transfer time. As a result, we designed our Sgm implementation using the described compute kernel and the traversal scheme, which demonstrates lowest data transfer time for high compute efficiency case, which here is the optimized outer product scheme. We will, however, show that even though large K-prime results in high compute efficiency, it does not necessarily result in best overall efficiency. Next, we will see how the compute and data movement parts are scheduled together. Our DMA schedule runs on the Leon OS that controls the DMA engine to schedule data movement and compute in accordance with optimized outer product traversal scheme. The DMA transaction lists are stored in the Cmx slices that are not tied to any shave. Separate lists are used for each matrix, and block loads and store transactions of a matrix for all shaves are chained together in a single list. Leon OS updates transaction lists concurrently to shave operation. Moreover, each transaction list contains a status field containing the status of transaction. For our implementation, we use double buffering for A and C blocks, to which Leon OS ensures conflict-free access using flags. DMA raises an interrupt when a transaction is finished for each list, after which the interrupt handler updates the status field. Here we see a time trace of our Sgm execution for one Cmx level B block. Since we use single buffering for B, its loading is not overlapped with computations. However, the loading of matrix A and C blocks, as well as storing of C blocks, is completely overlapped with the kernel execution. So that was our implementation. Now moving on to the results. First, we see the DMA performance. Here, table on the right shows measured bandwidth for data transfers for different matrix sizes using the best performing Cmx slice block dimensions, 12 shaves, and a burst length of 8. We modified the Movidius provided DMA driver and streamlined it, which resulted in an overhead reduction of 400 clock cycles per DMA invocation. This modification also resulted in an average 2% improvement in DRAM bandwidth. As we can see, our implementation achieves more than 70% of peak bandwidth for loading matrix B, 81% of peak for loading A and C, and 92% for storing C back to main memory. Overall, our implementation achieves 80% of the peak DRAM bandwidth. Next, we study the effect of matrix block shapes on DRAM page faults, which are costly in terms of time and energy. The dimensions of DRAM on Myriad 2 are shown here. We estimated the page faults by mapping memory accesses of our optimized outer product algorithm to the physical address space of the DRAM. Figure on the right shows normalized page faults for different block shapes for matrix size 4800. We will mainly focus on two K-prime values, that is K-prime 1600, which minimizes the compute time, and K-prime 960, which minimizes the overall time. Notice that compared to K-prime 1600, the K-prime 960 results in an increase in total compute time by 0.22%. However, for the K-prime 960, we notice a 3x reduction in data moved between CMX and DRAM memory, resulting in a 67% reduction in the data transfer time. It also resulted in a significant reduction in page faults for all matrices, and overall a 65% reduction in page faults was noticed. This tuning of matrix blocks to trade off compute time with data transfer time resulted in an overall performance improvement of 6% compared to K-prime 1600 and a 4% improvement in energy efficiency. We now show the performance and energy efficiency for best performing block shapes for different matrix sizes. Our implementation achieves a peak performance of 46.36 gigaflops, which is 92% of the peak Myriad 2 performance. It also achieves an energy efficiency of 25 gigaflops per watt at 1.8 watts power dissipation. It is important to notice that the power consumption for Sgem is 50% higher than the TDP. As such, TDP could be in many cases misleading. Our implementation also achieves a 11% and 13% higher performance and energy efficiency compared to a direct port of Myriad 1 code to Myriad 2. Next, we show the effect of strong scaling. With more shaves, the DRAM bandwidth improves and levels off at 6 shaves. Similarly, the data bus utilization peaks at 40%. The arithmetic intensity increases with more shaves due to the data reuse offered by the Cmx Level Kernel. As a result, the amount of data moved between Cmx and DRAM decreases as more shaves are employed. We also provide comparison of the energy efficiency for Myriad 2 with different architectures. As can be seen, the Myriad 2 outperforms all the shown architectures in terms of energy efficiency. Finally, to summarize our work, we demonstrated a highly efficient Sgm implementation using DMA and double buffering on the Myriad 2 chip. We showed that for block shapes resulting in high compute efficiencies, an outer product block traversal scheme is better. We also showed that 12-core Myriad 2 achieves significantly high energy efficiency than several other architectures. Finally, we would like to acknowledge the Intel Movidius staff members who helped us in numerous ways, the University of Houston, and members of our research group, ACRL. We thank you for your attention, and we welcome any questions.
Thank you very much, Suyash. Any questions for him? You can open the mic and ask.
Sorry, I just want to ask about the generalization of your approach, because you are using Sgm. Let's say it's kind of regular application because you have regular memory access. What will be the case with an application which experience an irregular memory access?
Could you be more specific in what you mean by irregular memory accesses? Sorry.
Where the stride is something which jumps in a very irregular way, because Sgm is a very regular. I mean, it's a linear algebra operation.
Right. Yeah. I'd like to point out that our approach was to show a basic methodology to analyze such applications. So we took Sjm as an example here. So the approach that we took to analyze the data movement and data transfer times, and also their effects on the DRAM page faults, and then working on trading off the data movement time as you have compared to what you have as a compute kernel. That's our main methodology of showing that how to approach an application. So.
Okay, so here Sgm is just a case study.
Exactly.
But you have to focus on the methodology itself.
Exactly, yes. So we emphasize more in our paper on these methodologies rather than just
the application,
just the results. Yes.
Okay. Okay. Thank you.
Yeah.
I have questions.
Okay.
Can you give us some description about your like language you use in programming and difficulties, particularly when you're dealing with memory traffic all around using Myriad 2?
Right. So the programming interface for the Myriad 2 chip is basically using C language. The Leon OS core that manages the whole chip, it can be programmed using C. It's based on Spark V8 architecture, so it has its own instruction set. And Movidius provides a compiler to compile C to that instruction set. As for the Shave cores, they also have, they are specialized core and they have their own instruction set architecture. And the compute kernel that we talk about is written in that particular instruction set. So we handwritten that assembly code for the compute kernel.
Great, thanks. I have a following questions is because at the moment you compare with this energy efficiency. Do you have roughly idea about time to solution compare here you compare with NVIDIA K40 and also E5?
Right.
So what's the time solution difference?
That's an interesting question. So obviously the NVIDIA K40 is a GPU. It has lots of compute power and it has order of magnitude higher performance than the Myriad 2. But the Myriad 2 chip was designed to work on edge devices and provide real-time vision processing capabilities on those devices. So here we mainly focus on the energy efficiency because on the edge devices, the energy efficiency is an important factor as compared to the performance.
Okay, okay, go ahead.
Sorry, I just want to know, I mean, compare with, you have this since you're doing Sgm, so I believe you can measure the time, how long it take with the same like matrices, so same size of matrices. Do you have roughly idea how slow, how far, like roughly compare? Have you compared this?
Well, as I said, the difference is at least 3 orders of magnitude.
3 orders. Oh, it's actually
right.
quite good, actually. 3 orders.
Right. Yeah. So as I said, it's a GPU, NVIDIA. So
I know. So let's just give it a graph like. Thank you very much.
Sure.
Okay, there's a question on the chat from Clisser Stelling. Did you consider sparse matrices?
No, for this implementation, we did not. It's completely, it works with dense matrices. But yes, sparse matrices would be an interesting subject, and that would require quite a lot of changes in the code, because the compute kernel as of now assumes the matrices are dense and just naively runs the compute kernel and the data movement strategy as well. So it's going to take quite a lot of more optimizations.
Okay, and a question from myself. Do you think if Myriad has more memory inside, it will be more energy efficient?
That's an interesting question. Yes, I'm not sure about the energy efficiency, because as you increase the memory, then you also increase the power consumption of the whole chip as well. And obviously, if you have more memory, you can store larger matrices and obviously can get more performance. You would also need to increase the on-chip memory as well, because you need to have more data on local slices. So that's what our approach is, to minimize the accesses to lower level memory. So yes, performance, yes, it will increase, but I can't definitely say anything about energy efficiency.
Okay, thank you very much. Any more questions?
Yeah, I just have one last question, but 2 questions is the same. It's a strategy. The first one is, I saw that you compare your work with the cell. Why comparing this with the cell? And the second question is, did you intend to implement your methodology as a kind of source-to-source compiler? Because you did it by hand. So are you planning to implement it in a kind of source-to-source compiler?
As of now, there are not such plans. But we do plan to use our insights that we gained using this case study to work on more complex problems, such as machine learning problems, such as the convolutions, which are quite widely used in machine learning algorithms. So not exactly a tool as you want to say, but yes, we would utilize those insights that we gain for a more complex problem. To answer your question about the cell BE, we wanted to compare our implementation for both type of architecture. And when I say both, it's first, since Myriad 2 itself is a heterogeneous architecture. So cell BE was one of the quite famous architecture that came out quite a while ago, obviously, but still it was very powerful at the time. We also compared it to the Texas Instruments C6678 DSP, which is also an interesting device. So those are the heterogeneous architectures. And to be fair, we also compared it to the general purpose architectures like the NVIDIA GPU and a Intel CPU.
Okay, any more questions? Okay, nice. Thank you very much, Suaj. Very good presentation. I think the workshop is about this, our discussions and everybody there talking about your work. And so right now we have an interval, probably lunchtime in Europe, breakfast time in Brazil. And then we come back 1 hour later with the next presentations. Thank you very much for the presence here. Thank you very much for the authors for the very nice presentations. See you later in 1 hour. Bye-bye.
Thank you, Christiana, for sharing this.
Which is hard for the developer to grasp and to maintain his cognitive memory, to keep all dependencies in scope. and inefficient parallelization due to hardware complexity, where it is hard to know all details of the underlying system and utilize them for the developer, where the compiler could use this but needs to be guided by the developer on his intentions. We want to provide an accessible framework which helps to communicate the developer's intentions, find a safe set of parallel tasks which do not violate their dependencies, and manage the complexity, and optimize the allocation of processing resources to those tasks for efficiency. The challenge of efficiency is that if you parallelize a program to the finest degree, you may incur a lot of communication overhead. If you don't parallelize it enough, you cannot utilize all resources of a parallel hardware. Rust comes into play here as implementation language, as it provides safe defaults. It ensures that there's only one writer or many readers at the same time for a resource or a memory location. That avoids race conditions, and it also avoids resource leakage, as it ensures that resources are properly freed at the end of scope. This all is analyzed at compile time, and Rust provides immediate feedback to the developer whether his code is correct in that regard. The standard library of Rust also provides for a bit more complex protocols like mutexes, channels, and reference counting, and it is also possible to build own custom parallel protocols, but still tedious due to the extended specification for lifetimes and to prove to the compiler how the resource usage is still safe if you use safe code. I want to introduce an example we use to better understand the work of our framework. So we implemented an aircraft telemetry processing application, which gets its data from a sensor network and builds an aircraft model that reconstructs position and velocity of the aircraft. For that, we receive datagrams from each aircraft via radio, decode them, and parse them into message object, which then can be routed to the specific aircraft context that does the stateful processing for like a small flight simulator, which may also give a model for noise or other emissions, or might also have a separation model for safety aspects, for example. We parallelize that using the fork join pattern, and to bridge between context we use shuffle. So here you see that we at first fork into the decode and parse stage. At the bottom you see on the corresponding system view, so to say, where the different tasks work with each other. The shuffle then goes from a set of tasks to the next set of tasks for the following stage, but now it has a selector based on the aircraft identification to do the routing right. And in the end, we have a join which may sort the messages according to timestamp, so that all the parallel streams get merged into one stream which is in order again. Our premise is that we build high-performance computing applications where the developer usually knows the workload and the system. It might change, but he has usually access and can optimize for the platform. And our framework has an automation to gather task execution times based on an example workload, to later on do an efficient allocation, and tries to minimize communication overhead using micro benchmarks that were executed on the target system. Here's an example for our system where you see that a simple Rust function call, which is synchronous, is just in the order of some nanoseconds execution time, whereas an asynchronous call for I/O purposes or to interact with services will be in the range of 100 nanoseconds. And the Rust channel, which is used to communicate between different parallel tasks, is just above 1 microseconds. So there is an order of magnitude in between them. But we can also show that the Rust channel is has slightly less effort than the classical MPI send call when we look at C. And the task farm, which incorporates a fork, a dummy task, and a join operation for 4 parallel threads, is just 3 times has 3 times the overhead than the simple channel operation. Using that for our example, you can see that now annotated with the lambda as input rate and mu as the throughput rates of the task forms above the task graph. We can see that the throughput after the allocation is slightly higher than the input rate. That is on purpose, as we do not want to stall the system. And below the task graph, you see the execution time for the different stages, which we gathered through profiling and statistical analysis. Based on them, we did the allocation with an iterative algorithm that allocates the next task to the task farm that is a bottleneck now. And when it discovers that the bottleneck is the input, the output, or another sequential task, it will stop allocation and avoid oversubscription. In our case, we allocate 4 tasks to the first task farm, 4 threads to the first task farm, and 6 to the last one. As a result, the optimal allocation will be 12 threads, which you can also see as a blue dot marked in the bottom of the graph, where we reach the input rate, or limited by the input rate. And when we would increase parallelity further, we would only increase the CPU time, which stands for the overhead we introduce. The scaling is quite close to the sequential when we would scale the sequential program time without the parallel patterns. We also did applied our method to the famous word count example, where you just take a huge text, split it into words, and count out the frequencies. The challenge here is to parallelize the central table of words and frequencies, which we solved so that we have different copies. The first task farm computes different copies of those tables and then shuffles them by the word name, merges the entries, and has to only sort the word list in sequential. The result of that process is that we scale better than Pico, which is a high-performance computing framework in C++, and better than an in-memory application written in Rust. We assume that we are better than the in-memory application because we have a better cache usage, because we do not load it, the data first into memory, but process it chunk by chunk. Thanks for your attention, and if you have questions, I'm glad to hear them. Yeah, so
thank you. So if you have questions, please feel free to ask. Open your micro or you write it in the chat.
And if you like, I also can say that I talked a bit on about the, or very less about the runtime. So we're using the Rust Tokyo runtime, which is an async runtime, and in future, we like to investigate on whether asynchronous runtime or how much the impact of synchronous versus asynchronous would be, and go a bit more into detail on latency modeling and energy efficiency. And of course, study the usability of our library.
I have one question. What is your motivation of using Rust that I didn't understand? Because I don't know Rust. So please, can you explain the motivation?
I did parallel programming in C and C++ a lot before, and also had my students do exercises with MPI and saw a lot of errors in that. And Rust has actually a very strict model of the usage of memory references and locations. So you may not, as I had in the slides, just let me check a moment. You have this principle that a variable or resource has an owner, and the owner may share the reference with others, but only with, give it away to one other for writing or to many for reading, but not both at the same time. And if you want to do something else, where multiple threads access a resource, you have to either signify this place as unsafe and ensure yourself that it is safe in the logic, or use other provided protocols like mutexes and channels to synchronize, but you cannot accidentally, so to say, create a race condition.
So your main concern here is correctness, not efficiency.
But still, Rust is quite efficient, as you saw in my results. But I wanted to start off at a safe language and then make it more usable than the original libraries are. And I can't prove that yet because I'm not, I haven't conducted studies on that, but still keep it efficient, so to say.
Mm-hmm.
But if you don't care about correctness and if you don't care about safeness, and you compare C++ with Rust, how do they perform?
It's more or less the same because they both compile directly to machine code, and they just use LLVM as backend. So I guess it depends on the operation and libraries you're using, but there should not be a theoretical difference.
Mm-hmm.
Okay.
Just another question is how large the data volume you are dealing with?
I guess I have it in the paper. I had different sets. I used usually 6 GB of input data, but for the aircraft example, I had also one with 21 GB.
Mm-hmm.
But it does not fit into the memory.
No, it's on an SSD drive. So that's also why I'm limited by I/O rate, and at some point in time, because I cannot, with a many-core system, I cannot sustain that. So for a real-world high-performance example, I would need to have some high-performance network device or storage, which I don't have at the time.
Mm-hmm.
Okay.
We have time for another question. I had another question about your, I see that in your curve.
Yeah.
Performance curve, yeah, I see a limitation. There was an asymptotic. Could you explain me this, please?
Which one? This one or the other diagram?
Yeah, even the last one, I see an asymptote.
So I don't know. Do you see my mouse cursor? So so Pico is a green plot which has more or less asymptotic behavior, but my version is a blue curve, And there you actually see as actually a need at 32 threads where we can't improve further on runtime. So it will even grow slightly after that because of communication overhead.
Another question. We have time for another question. Okay, thank you very much. Let's switch to the next talk. Maybe we have 2 minutes, depends up. Ziyang is Shizang, re-evaluation of atomic operation and graph coloring for unstructured finite volume GPU simulation. Okay, so you have 15 minutes and then we will ask questions.
Zhang, just a question. You will make a live presentation or I have to stream your video?
You have his video. Do you have it?
I have the video of Zhang.
I think video probably is the best option.
At the moment, he's streaming, sharing his PowerPoint. I don't know if you prefer to make a live presentation or if you prefer that I stream his video. Zhang, can you
answer?
Okay, I will.
Okay.
Zhang.
Okay. Sorry. I forgot opening the speaker.
Okay.
Sorry.
You will make a live presentation?
It's okay. Just better.
Or you prefer I can stream your video? It's your choice.
Some trouble in CFD applications. In CFD applications, as a computational whole domain is divided.
I think you could stream the video.
Yeah, I guess, yeah, you can do the video.
I think it's better.
Okay.
A boundary control volume is called phase. For unstructured mesh, volumes with adjacent number do not mean the physical connectivity. And so the volume index is often stored in the order of the phase index. For example, the volume index O can be represented by owner
Okay,
FR.
I will share the video.
Volume index P can be
But I'm hearing some voice behind.
Okay.
Okay,
Is it
I will
out?
begin to share the video.
Okay.
Okay.
Hello, my name is Xi Zhang. I'm from National Supercomputer Center in Guangzhou, Sun Yat-sen University. And the presentation is re-evaluation of atomic operations and graph coloring for unstructured finite volume GPU simulations. Xiaohu Guo is the corresponding author from Hartree Center. The presentation contains 4 parts, including background, a mathematical model, algorithm, and performance, and the conclusion. GPU has played an important part in computational fluid dynamics, and many CFD applications has been accelerated by a GPU. GPU's multiple threads can run simultaneously for calculation of operating data. The characteristics brings some trouble in CFD applications. In CFD applications, the computational whole domain is divided into non-overlapped arbitrary control volumes. A boundary of control volume is called phase. For unstructured mesh, volumes with adjacent number do not mean the physical connectivity. So the volume index is often stored in the order of the phase index. For example, the volume index O can be represented by owner Fi, and the volume index P can be represented by a neighbor Fi. Besides irregular data storage, the access to volume data can be indirect. For example, the variable rise is located on the center of the volume. The rise on the volume O can be directly as RESO or can be indirected access as RES owner Fi. So physics could do store operations on the same volume when considering multi-threading implementations importing to GPU. Data races can be induced and could be and should be resolved carefully. Four methods can be used to address race condition in CFD. Firstly, auxiliary array can be used to address race condition. However, much more additional memory should be used, so it is not good for large-scale simulation. Secondly, volume loop can be applied to replace phase loop. However, there are redundant calculations for all phases. Thirdly, graph coloring can be used. By graph coloring, phases are divided into many groups. In one group, any two phases will not be belonging to the same volume. Graph coloring have good possibility and excellent performance for CPU. The fourth method is atomic operations, which is supported by hardware. It is generally considered that much more expensive atomic operations are much more expensive. However, the situation may have changed with significant atomic hardware performance improvement since NVIDIA and Kepler GPUs. So, graph coloring or atomic operations, which is better in unstructured matched CFD, is what we want to study in the paper. In order to do the research, the CFD a computational software framework called NW Finlay is used, which is one part of a national numerical wind tunnel. NW Finlay owns many functions and models. In the research, we only consider unstructured mesh and high-speed compressible flow. So the compressible Navier-Stokes equations are solved. The vector Q contains 5 different unknowns. By dividing the computational domain into different volumes, the form of the compressible Navier-Stokes equation is changed into the discrete form. It can be seen that many calculations are on the phases, so the race condition should exist too much. In fact, from the computational procedures, it's shown that there are many race condition operations from R1 to R6 and include add, min, max, different race condition operations. From the executing time proportion, it is shown that more than 50% of computational time is related with race condition operations. So we choose two typical algorithms for research. The algorithm 1 shows flat summation on RES. Flats is located on the face. GPU threads on different faces may update the same RES on the volume. For example, GPU threads on Fi, Fj, Fk, Fl, Fm, Fn may update the same RES on volume O, which induce the race condition. The algorithm 2 shows the maximum pressure determining pressure is located on the volume center. So GPU threads on Fi, Fj, Fk, Fl, Fm, Fn may update PL max on volume or instantaneously. So they will induce race condition. In order to study different algorithms for resolving race condition, we choose Arena M6 for test cases, and we choose 5 different match sizes, and the simulations are performed on NVIDIA Tesla V100. Firstly, we use atomic add to resolve race condition for flat summation. The implementation is easy. Just use NVIDIA supported atomic add function. We tried shared memory optimization for increase the locality of the flats. However, the results show that the shared memory has no effects on the performance. Then we study the atomic operation for a maximum pressure. The atomic mass function is used. We also tried shared memory for optimization. By the comparison, it showed that the shared memory is no use for the increase of the performance. And then we studied graph coloring for a flat summation. We applied a greedy-based algorithm to divide faces into several groups. It can be seen that the face group in the same face group is computed concurrently in a GPU kernel. However, GPU kernels for different face color groups have to be run in series. We try reorder volume face, reorder flats, and shared memory in the 3 methods for optimization. Shared memory is used to increase the locality of flats. As a reorder of volume and phase index can guarantee the data data RES coalescing in the largest phase group. The reorder flats can make flats coalescing on faces. Normalized time shows that the reordered flats can increase the performance significantly, almost the shared memory has no effects on the increase of performance. The volume and the phase index reorder make negative effects. And then we study graph coloring for maximum pressure. We tried to optimize the methods, including shared memory. and reordered volume and phase index. By the normalized time, it shows that both reordered volume and phase index and shared memory will not increase the performance. Finally, we compare atomic operations and graph coloring. For flux summation, we compare atomic operation with no optimization and graph coloring with reordered flux. It shows that it shows that atomic operation is more efficient for all of the mesh sizes, and the gap between atomic add and the graph coloring becomes smaller with the increase of the mesh size. But atomic add is still 2 times faster than graph coloring. For local mass pressure determining, atomic mass with no optimization and graph coloring with no optimization is compared. With the mesh size increase, the performance gap between two implementations is increased until mesh size fall, and then slab dropped around. So all required performance kernels are re-implemented with atomic operations and compared with 18 MPI CPU code. Around 4.8 times speed up can be gained. Then by the research, it concluded that the overall speed up of the current single GPU implementation is around 4.8 times, comparing with the 18 MPI tasks on CPU for different mesh sizes. And our performance results have demonstrated that the atomic operations has better performance than graph coloring, and atomic operation is easy to implement and maintenance. For the general unstructured FVM application, using atomics instead of graph coloring for GPUs after P100 has achieved 2 times speed up. Finally, we do need to reevaluate the best approaches for new GPU architectures released by NVIDIA, AMD, and ARM in the future. Okay, thank you for your attention.
Okay, thank you very much for this nice video. So we have time for questions. If you have question, please.
I do have one. Can you generalize your results for atomic operations versus graph coloring for other applications?
No, I just used the atomic operation after the research. In fact, in most times, the atomic operation is more efficient than graph coloring in my application, in the safety application. Okay.
But do you think something general?
Can I give a compliment answers for what you just said? So yes, I think what we're trying to do is general, like for unstructured mesh application, and you do come across different kind of like what do you call that, mesh connectivity information. So that's the key things we need looking at. So that's why when we actually trying to do the test, because we use these called hybrid meshes, which basically have triangles inside, also have other kind of different topological inside. That gives basically almost covers the different connectivity information in there. So in that sense, from the like input case, we definitely represent the whole range of mesh-based information there. That's one thing. Another thing is we're particularly concerned about whether For atomic and compare with which generally people want to use, people want to break the data dependencies for multi-thread programming. There's two basically general algorithms. One is using atomics, another is using graph coloring. So in order to avoid the naive optimization, so we basically try like quite a few things, just make sure we are not in that situation. So in that sense, yeah, that's another thing we take care of. In that sense, so we do have some generalization in there.
Okay, thank you.
Thank you. Another question, remarks, observation?
Yes, I have a question. I would like to know if they try to use different interconnection meshes, because they use a 6 phase. So I would like to know if they intend to experiment with different meshes.
So in this input mesh, we actually have mesh input is not just like one uniform mesh. It's unstructured mesh with different like hybrid meshes. So in that sense, we kind of take care of almost every kind of situation.
Okay, I understand now. Thank you.
Okay, thank you very much. I just have another question. Is in your performance result for the GPU, did you count the time for bring the data to the GPU, or is just the performance at the GPU level?
Just the computing time in GPU. We don't consider the data transfer, the time consumed by data transfer.
No, I think one key thing we have done is for within one time steps. No, within a simulation, all the time loop is purely carried on the GPU now. So we only do the transfer during the beginning of and then at the end. If you do the checkpoint, then there will be another transactions, communications. So the all optimization is based on trying to already have maximum reduce your reduce the number of communication between hosts and devices. So in that sense, we at the moment we only concerned because of breakdown the dependencies. But what you're concerned is right. But when we to evaluate about the total runtime, it does just all the GPU, but we didn't really counting like for initialization and finalization. So we didn't really count that.
Okay.
Yeah.
Okay. Good. Let's move. Thank you very much for this nice presentation and interaction. So let's move to the next talk by José Rufino, extending heterogeneous application to remote coprocessors with Opencl.
Okay.
José?
It's a stream or a live session? What do you prefer?
It's a stream, please.
Okay.
Thank you. Hello everyone, my name is José Rufino. I'm going to present the paper extending heterogeneous applications to remote coprocessors with our Opencl. This was a work done together with Rui Alves. This is the outline of the presentation. I will start by providing the context and motivation for this work. Then I will give details on the architecture of our Opencl implementation. Results of a preliminary evaluation will also be shown. Related work will be covered if there's enough time. Finally, I will lay out the main conclusions and future work directions. Let's start by introducing the concept of heterogeneous computing system. So this is basically a system where the main architecture, embodied by the familiar general purpose CPU, is accompanied by coprocessor devices that are typically of different architectures. These coprocessors usually include graphical processing units, FPGAs, or digital signal processors. And these coprocessors are, in a heterogeneous system, exploited beyond their primary original goal in order to accelerate execution of general-purpose computational demanding applications. In order for heterogeneous systems to be efficiently exploited to accelerate the execution of applications, special programming models are needed. Low-level programming approaches for the programming of heterogeneous systems include NVIDIA, CUDA driver, and the Opencl open standard. In these approaches, heterogeneous applications are non-single source. This means that they are made of different code components that target different architectures. So the host code creates the data structures to interact with the coprocessors, and the coprocessors execute specialized kernels of code. Originally, both the CUDA and Opencl programming models target a single node. This means that an heterogeneous application developed under these models can only exploit the coprocessors that are directly attached to the node where the application is started. And of course, the number of local devices that are attached to a single node is necessarily limited, which in turn limits the potential for application acceleration. Meanwhile, several alternatives for scaling out the execution of the heterogeneous applications to external coprocessors have been devised. One of them, a low-level approach, basically exploits InfiniBand networks to allow data exchanges between the GPU memory in different nodes. This is the approach pursued by the NVIDIA GPU Direct RDMA and the AMD ROCm RDMA implementations. At a higher level, there is also the possibility of extending the original programming models of CUDA and Opencl to expose the remote accelerators in their runtimes. Our CUDA and several Opencl-focused approaches, like our Opencl, pursue this path. Before moving into the architecture and implementation details, it is perhaps useful to state some of the main characteristics and design decisions of our Opencl. This will allow to better understand what comes next. So one of the first decisions was to make our Opencl network portable, that is, not dependent on any special network technology and only requiring TCP/IP to be available. This network portability is also visible in the choice of the ubiquitous BSD sockets for the communication layer. Of paramount importance is also the decision to support the running of binary precompiled Opencl applications without requiring the source code or any modification to it. Finally, compared to CUDA, we found Opencl to be more motivating for this kind of work once it is an open standard and supports other coprocessors besides GPUs. It is also important to clarify a crucial difference between our Opencl and similar approaches related to the Opencl platform concept. An Opencl platform is an implementation of the Opencl specification. So, a platform from a hardware vendor targets devices accelerators from that vendor via specific drivers supplied by the vendor. Our Opencl explicitly exposes remote platforms individually to an Opencl application, which then chooses the ones to use, and is also responsible for doing their load balancing. In turn, other related approaches unify all remote platforms into a single virtual platform, hiding individual remote platforms from the applications. This is done to allow automatic load balancing of the distributed device set. Moving on to the software architecture of our Opencl, it builds on two main components, a local vendor agnostic driver and remote services. The driver, also called an installable client driver, is made of an ICD file that is placed in the same folder as the vendor ICDs, so that the Opencl runtime, namely the ICD loader, can load the related R Opencl shared library. This library will forward Opencl calls to the remote services. Remote services sit on top of their local Opencl platforms, to which redirect incoming Opencl requests received from an R Opencl driver. It should be noted that this architecture is compatible with any number of client nodes and remote nodes operating simultaneously. Okay, so now let's have a look at some details of the implementation. How are connections between the driver and the services managed? Well, for starters, TCP is currently used for all communications, and in order to optimize performance, the driver keeps a record of previous connections so they may be reused. Okay, so we found that a new connection for each Opencl call would severely harm performance. At the services, we have the POSIX threads handling the client connections. So every time a new connection arrives, the front-end thread assigns that new connection to a worker thread. In turn, the worker thread will forward the Opencl request to the underlying Opencl platform. We also took care of connections cleanup, so when an Opencl application ends, all OpenSocket descriptors will be closed, and this makes all remote worker threads previously paired with the application to unblock and self-terminate. How are services discovered by the applications? This is done at the startup of the application, the client node. And the first application thread that tries to query the platforms exposed by remote OpenCL will learn the IP addresses of the services from a host file, and the connections established with the services will be later reused. A critical issue that must be tackled in any remote procedure call platform is how to match the local objects seen by the application with the remote instances that are created at the services to support the intended actions. The same issue arises in our OpenCL. Other approaches just create local fake pointers for each valid remote pointer. But in our OpenCL, the tight integration with the ICD loader prevents this because the loader needs to deal with valid local pointers. So for every remote object, there's a twin local object, but this is not a replica. In fact, it only matters that its local address is valid. The mappings between local and remote pointers are kept in the same dictionary that is used to manage connections. An important detail is that this object management only concerns OpenCL API objects and not user-level data once this is fully transferred between the application and the services. In our OpenCL, concurrency management is needed just in a very few specific situations. At the driver, the data structures used to manage connections and object pointers are protected by a simple multiple readers, one writer locking mechanism. This is enough to support multi-threaded client applications. At the services, multiple working threads may be placing OpenCL calls on the underlying platforms, and locking is only needed in a corner case. This is because, per the OpenCL specification, all but one OpenCL API functions are thread safe, and implementations are expected to honor that requisite. This slide is about how remote OpenCL manages contexts. We will skip the details on that for now. It also mentions a specific OpenCL extension that allows OpenCL applications to know the location of remote devices so they can implement their own load balancing mechanisms. So we move now to the presentation of some results of a preliminary evaluation of remote OpenCL, but before that we show the current API coverage of remote OpenCL. So it supports approximately 71% of the OpenCL 1.2 API. Image and graphic primitives were left out, as is usual in these kinds of approaches. So with regard to the computing primitives coverage is very high, approximately 94%, with some exceptions. And despite these exceptions, this was found to be enough for most computing benchmarks and applications. So in this preliminary evaluation, the goal was to execute some reference OpenCL benchmarks to test the compliance with the standard of remote OpenCL, to execute at least one real-world application to demonstrate usefulness, and also to gain insight on the overhead of remote execution. We can see the tests selected on this table. So we have a mix of tests that stress different subsystems, either compute or memory bound. They are all open source to ease the instrumentation and automation. They are actively maintained in the last few years. Most of them are mono-device, means that they are only going to be able to use a single coprocessor, except for hashcat, and they represent a mix of synthetic benchmarks and real-world tests. Here we can see the characteristics of the computing nodes that hosted the coprocessor that we have used. Basically, we have used an overall of 4 GPUs placed in 2 nodes, so 2 GPUs per node. The methodology used to test was very simple, so let's go on to the results. So the first results are for the Babel Stream benchmark. This benchmark is made of several sub-benchmarks that test the memory bandwidth for 5 kernels. On the left chart we can see the specifics about each sub-benchmark. On the right side we can see that the local execution of this benchmark took 6 milliseconds, but the remote execution 26, so this entails into a remote overhead of more than 300%. Another benchmark that stresses the memory subsystem is CLMEM. So basically this performs a sequential write, read and copy of 128 gigabytes of data. This is done by groups of threads. The data is generated on the fly in the GPUs, so the network intervention here is very small. And we can see precisely that here, because the difference between local execution and remote execution is minimal, so a very, very small overhead. CLPeak is a benchmark that stresses both device memory and processing elements. So we can see here global memory bandwidth, single precision, double precision compute, and integer compute, transfer bandwidth, and also kernel launch latency. So there is a variety of results, low overheads, more higher and moderate overheads. So it really depends on the benchmark. Bench is a more interesting benchmark because it's related to real-world applications. In this case, we have results for two sub-benchmarks, the Black Scholes analytic and the Monte Carlo simulations. And aggregate combined, they yield a remote overhead of approximately 20%. The last results are for a test made with Hashcat. This is an advanced password recovery tool, relatively known. In this case, it was used to perform a dictionary attack with rules to recover passwords from 28 MD5 hashes. And Hashcat was tested in several different scenarios, each one with a different number of GPUs, from 1 up to 4, covering different combinations of local and remote GPUs, as we can see in this table. So we see what happens, how much time does it take to recover the passwords into a single remote or 2 remote GPUs. Then we move to a single local, then 1 local and 1 remote, 1 local and 2 remotes, 2 locals and 1 remote, and finally 2 locals and 2 remote GPUs. And we can see from the chart that there are always performance gains as we add GPUs and we move from remote to local, and the combination of local and remote. And so this is an interesting case that shows how remote OpenCL can be used to accelerate a real-world application. Looking back at the test results, so as expected, remote execution introduces overheads, but the order of magnitude of these overheads will really depend on the test's specifics. So as expected, if we have compute-bound tasks with very little data transfers between hosts and devices, this will take better advantage of remote OpenCL, and the opposite is also true. There are also some details that may affect the outcome of the tests, but we will skip that for now. We will also skip details on related work, and we will come back here later if needed. And so we have introduced the remote OpenCL, a novel implementation of an API forwarding layer that allows OpenCL applications to use remote network connected OpenCL devices. It has a certain number of interesting characteristics. So as we already said, we can run binary OpenCL applications. It integrates very well or perfectly with the OpenCL runtime. It's network portable. And it exhibits small or acceptable remote execution overhead for many use cases. So there's a lot of future work that we plan to conduct, and perhaps the main aspects are some scalability studies and some performance comparisons with related approaches that are already in progress. So questions, doubts, I am available. Thank you for your attention. Good afternoon, everyone. My name is José Rufino. I think there's no need to repeat that.
Thank you very much, José. So, thank you very much, José. So we have time for a question.
Well, I have questions. So what would be your ideal scenario to use your OpenCL for real applications?
Perhaps embarrassing parallel applications. Okay, that depend on GPU. So if you have an application that has a very few network transactions, or they are concentrated at the beginning and at the end, I think it will work very well. But it really must be accessed on a case-by-case basis. That's what we saw in the benchmarks. So it's not a panacea or a good solution for every problem. It's far from it. But it's interesting because in certain use cases, you can take advantage of coprocessor resources that are in a cluster, for instance, or even in any available in any TCP/IP network. One of the scenarios that we have not yet exploited, but it's by design, it's there, is to access a coprocessor with routing involved. Okay, it's TCP/IP, so it's going to work. Another one that is very interesting, and we really intend to evaluate it, is one that is related to virtualization. So we know that there are certain kinds of GPUs, very expensive, that can be multiplexed very well by several virtual machines. Okay, but we using these kinds of approaches, we can have some GPUs installed on the physical server. So we have some virtual machines there, and we can basically, instead of assigning a virtual GPU, we can expose the GPU that is on the server to the virtual machines that run there. And of course, our expectation is that the overhead will be much smaller than going through the external network.
Thank you. Now, since how you actually do this too, so another approach, like you could use MPI with Opencl together. Do you think what's the advantage to avoid using MPI instead of using your network implementation?
So you are asking why we didn't use MPI, for instance? Did I understand? Okay. I know MPI. I have already used it, and this is something that is not in the paper for obvious reasons. But I also was part of the team that worked in Opencl. Okay, and that one that was developed in 2012, so a few years ago, like 8 years, used OpenMX. That was a very low-level communication layer, basically. In terms of API, very similar to MIDINET. And our expectation was by that time, okay, let's try to minimize the weight of the network as much as possible. Okay, so we see sockets as something very, very pure. Okay, very, very, very specific only to that end. So we didn't find the need to use, for instance, collective operations or other advanced features that MPI could provide us. And in fact, for pilot work, we also intend to revisit the communication scenario. We have already conducted some comparisons with other approaches that are referred in the related work, and we found that we are almost faster than all of them, except for one that used async I/O. It also used sockets, but it used async I/O. Right. Also, we are going definitely to take a look at it. Okay, so.
Thank you very much.
Okay, thank you, Jose. So maybe you move to the next talk. Given by Vittoria Pino, OpenMP tracing, easy profiling of OpenMP program. Vittoria is there?
Hi, I'm there.
Okay.
I will streaming the presentation.
Perfect. So it will be a live presentation, no?
Yes. No, it's streaming.
Streaming. Oh.
Yes. At the University of Campinas in Brazil.
Okay.
Today, I will refer to the article on OpenMP tracing, a profiling tool for OpenMP applications. This is my undergraduate research working with my advisors, Hervé, Márcio, and Diego. First, why do you need to use a tool for profiling parallel applications? Well, parallel codes are usually difficult to debug, and the more complex the application, the more difficult it is to understand the behavior of the code. Profiling tools can analyze both the behavior and the application code, showing time, of memory spent. For example, if you show how much time is spent on each function of the code, how many tasks were created, how much time the program spent on memory transfer, and so on. In this way, a profiling tool is very useful for debugging the code, analyzing its performance, and detecting bottlenecks and overheads. Therefore, allows the program to optimize its application. So, the goal of community tracing is to be a lightweight profiling tool for community applications, and to be simple to use, analyzing both the time and the behavior of the application, without the user having to inject code into your application. Now, I will present an overview of the tool. Finite tracing generates two files: a graph that represents the tasks of the application, and a timeline of the OpenMP events, which is visualized using a Chrome extension tool. The profile information generated by the trace comes from the OpenMP runtime, more specifically from an API called OMPT, that communicates with the user application through callbacks. I will go into more detail in each phase of this process in the next slides. OMPT, the API used by tracing, is part of the OpenMP standard. It provides notifications of OpenMP events that occur during the execution of the application, and allow us to build tools that examine this information. So, the tool instead is OMP tracing, and we register some callbacks which provide to retain this information. However, it is necessary to indicate to the MPT that the tool exists, so that the MPT will keep the information of the application stretch. There are several ways to do this, but with OMP tracing, it is only necessary to compile it as a library and indicate the library path in an environment variable. Later, I will show how to do this. Here we have some examples of OMPT callbacks that can be registered, such as the begin and the end of the parallel regions, the creation of the task, the creation of dependencies, and so on. Well, now I'm going to talk about what OMP tracing does with the information provided by OMPT. So, the application user first chooses which callbacks they want to register through a JSON file. There are two ways to pass this file to OMP tracing. By
Está a ouvir, não, professor? Para não?
Something happened.
Victoria, we lost your sound. If you prefer, I can share.
Yeah, but please, your video, no, your
sound.
So yeah,
your sound is a little bit dirty.
The sound doesn't work.
If you prefer,
your micro. Turn off your micro.
Okay, and try to share.
Muting my microphone.
Okay.
Because there is an echo.
Yes. When you click on share, you have to share the sound of your computer and mute your microphone, your mic.
Okay, I will put put it again.
If you prefer, I can share your video. I have your video here. It's the same.
I'm sorry?
It's the same video that you have sent
to
Slack. Okay,
video.
I will share your video. Okay, just a moment, please.
Okay. Thank you.
No, no problem. It's on the 5 minutes. Okay. Okay. 5 minutes. Okay, just a little bit. Okay, here.
At the full selection. Thus, IMP tracing registers these callbacks and selects some information that IMPT provides to generate a timeline, also in JSON format, registering the time for each event. This timeline can be viewed in a Chrome Google extension tool called Tracing. Now, an example of the timeline. These horizontal colored bars are the events registered. In this left panel, you have the categories of these events divided by threads. To select some event, you just need to click on it, and more information about this event will be present in this panel below. Now, an example of the graph generated. It shows these tasks with the start and the time and the total time spent. And it also shows its dependencies. Now I will show a demonstration of the use of IMP tracing. This is the compiled IMP tracing library, and it's necessary to indicate its path to IMPT. So it is necessary to assign its path in the environment variable IMP to libraries. After executing the code, the timeline and graphs were generated. This number in the file name is the corresponding process number. This is the graph generated with 3 tasks. Now, it is necessary to open the browser and enter the tracing URL. And this is the timeline generated. There are some events like the thread region. If you click on
What's happened? The code is running, or there is something? Okay.
Now I'm going to pass a callback selection file through the environment variable IMP tracing config path. Recalling that this variable is
So there is a technical problem. Do you read that?
And the new timeline was generated.
Sorry, I think it's the network.
And finally, there are many more events than before. For the experiment results, we use the task bench, which is a parameterized benchmark designed to explore the performance of parallel programs in different. You can currently use 17 different program systems. It allows you to explore several dependency patterns between tasks, including stencil, FFT, trivial, and others. You can also configure the kernel you use as compute bound, memory bound, etc. In your tests, only OpenMP was used, and the kernel used was the BusyWait with 1 billion interactions and 4 working units. There are 2 other parameters that you can configure: the degree of parallelism and the number of steps in the time. Well, first, we selected all the callbacks and executed with the stencil pattern, using for both as a degree of parallelism and as a step, and we got this timeline. However, because it has a lot of information and we wanted to analyze only the tasks, it was selected just the tasks callbacks, and that was the result. You can see here that 4 threads were created, which is the work units parameter. For the stencil patterning, the number of tasks will be the multiplication of the degree of parallelism by the steps. So, as both have a value 4, 16 tasks were created. Here in the picture, task 13 was selected, and its dependencies are listed below. But it is not very clear to see the dependencies like this. Thus, with the graph, it is possible to clearly see the generated dependency patterns and if they form the expected patterns. In the left, we have the dependency pattern generated. And here on the right is an example of changing the step parameter of the task bench, and as it changes the graph design. In this case, the steps were changed to 6, and this increased the graph height by 2. Here we have other examples of other task patterns that we generated. This is FFT, this is DOM, this is all to all, and this is the no-con. Finally, here is a table comparing the impact of IMP tracing on the execution time of task bench. This execution time corresponds to the average of 5 measures, and the variation represents the overhead in percent to the execution time when profiling with IMP tracing. This variation is almost 7% for 256 tasks executed in about 5 minutes, which indicates that IMP tracing is lightweight. Well, the conclusion is that IMP tracing can be very useful to analyze the performance of the application. In addition, it is light and simple to use. without needing to inject code on the application. Now, I finished the presentation and I would like to thank you for your attention.
Okay, thank you, Victoria. And then we have time for a question.
Claudia, I have a question. Victoria, imagine an application with hundreds of threads dependent one of each other. Does the tool support a graph with this feature? What would the visualization look like?
With hundred of threads or hundred of tasks?
Thread,
because the graph is just about tasks.
Tasks.
I already tested with 200 and it works, but I'm not test with more than that. 200 works.
Because I imagine a lot of tasks, a lot. So how can we visualize with this tool that you are proposing?
The tasks can be visualized as a dot graph, and as a dot graph you can zoom it, and but in the tracing timeline it will be hard to visualize it.
Okay, thank you.
Another question. I was wondering if your you can work with pthread program, because you say OpenMP, but why is it important that it has to be OpenMP? If I implemented my multi-thread code with pthread, is it able to use your system to profile it?
I did not test with pthread, just with OpenMP, so I don't know if it works.
Okay. Because you are working directly with the code, even you don't even need the source code. So you are working with the compiled version of the code, isn't it?
We use the OMPT that is part of OpenMP, so I think with pthread it doesn't work.
Okay, okay. Another question, remarks, observation?
I have one question. Are you familiar with the Linux tracing tool perf and its event output? And I don't know, maybe you can say something to that. And they also have this time chart tool. I don't know if you have come across.
I'm sorry, I didn't understand the question. Can you repeat, please?
If you have an maybe scene or an adapter for the Linux tracing tool perf, so PERF, because they have a similar notation for tasks in a subtool which is called time chart. If you don't know, I'm no problem, but could have been because I used it.
No, I didn't understand. I'm sorry, my English is not too good. I didn't understand. Can you type in?
Maybe I think that the question is like a comparison. How do you position yourself compared to other profiling tools?
Yeah. How I can compare with other profiling tools?
Yeah.
About
because other
time, about
no. Because there are other tools also to profile OpenMP programs. There are other.
We don't have any. Please continue.
No. The question was How do you position yourself compared to other profiling tools for OpenMP programs?
We don't need comparing time with the other profiling tools, but we just make some tests with time with OMP tracing. So the OMP tracing doesn't interfere so much on the execution time, and other profiles too have other events to measure that OMP tracing. So it depends what you want.
Ah, okay. Okay. And do you have an example, even personally, of a case where the output of your framework was able to help the programmer to improve his program?
I think with OMP tracing, you can detect bottlenecks in your code to see when you spend more time. And you can use it to visualize it if the pattern of your dependencies were writing correctly. So it's a form of your debugging your code too.
Okay, perfect. Thank you very much. So this close this session, the second session of Wamca. Thank you all of you. Now we are moving to the third and last session that will be chaired by Clicia. Thank you, Clicia. See you now.
Okay.
Thank you, Victoria.
Good afternoon for everyone. So let us to start the section 3, the last one of Wamca. And the first talk will be done by Diana Barros. And the title of the paper is Analyzing the Loop Scheduling Mechanisms on Julia Multithreading. Julia, can
Diana, okay. I'll share my screen. 1 minute.
Diana, when you share your screen, you have to choose. You have an option on the bottom left, and you have to choose "Share my computer sound."
Button.
Okay, you have to cancel the sharing, please. Okay, click on the share again, just one time. It will open a box, a window.
Oh, sure, I see now.
Okay.
Hi everyone, I'm Diana Barros and I'm here to present my work with Sjm Implementation. It is analyzing the loop schedule mechanisms on Julia multithreading. So our work is based on Julia programming language, a recent dynamic language that was proposed to fill the gap between the needful performance, usually obtained from languages like C++ and Fortran, and productivity from high-level environments like Python and MATLAB. Julia was designed since the beginning to be a high-level parallel computing language, but only on latest versions it has become stable on multithreading, especially after version 1.3. And for this reason, there are only a few studies on the topic. We decided to study the multithreading functionalities on parallel loop iterations. Even though the loop scheduling problem has been widely studied on OpenMP, for an example, not much is known about Julia's loop scheduling, since it is dealt by Julia's internal scheduler, and the programmer still can choose the loop scheduling strategy. So, why Julia? Despite this high level build that it has, the high performance it provides make it even more attractive to scientific computing. Some of the reasons are here. The type inference mechanism, it distributes the type representation of all of the code and is mostly static. It avoids the allocation of variable size heaps and dynamic checks. It also reduces the need for JIT compilation and takes advantage of the LLVM optimization passes. There is also multiple dispatch that allows functions to behave differently according to all of their parameters. This is different than the method of overloading, where there is always an implicit argument that is always the same, which is the receiver, or what we usually refer as self, the instance object. And metaprogramming, that is Julia inheritage of Lisp. The most known feature is the macro feature, which contains a piece of code that is evaluated at parse time, reducing the runtime overload. Another way to increase performance is making use of parallel computing, and Julia offers distributed and shared memory programming models. The assignment of work to threads is done for tasks, also known by other names as symmetric coroutines or lightweight threads, etc. When a task is created, it doesn't start running right away. You must schedule it, and the output can be retrieved with fetch. And if you want to wait until it is done, just simply call wait, like we can see in this piece of code. Here we create a task. It will just wait for 5 seconds and print done. So when we call it, it doesn't stop running. We have to call schedule, and if we want to wait it until it's done, we just simply call wait. Julia provides a multithreading interface in order to facilitate the thread usage. The number of threads you could benefit from must be defined before running it, and it's done with the environment variable Julia num_threads. Latest release, version 1.5, makes it possible to define it with command line option -t. As for the implementation, there are two built-in macros: the threads, which has been part of the language since earlier released, and spawn, a feature introduced in version 1.3 in the middle of 2019. They both belong to the threads package and shouldn't be confused with the distributed spawn macro. The add threads macro must be used on a for loop, and it creates a task per iteration and distributed equally among threads. We can see it here. We have a loop with 12 iterations, so we can see that the tasks are distributed equally among the threads. Each thread has 3 tasks. After this work was finished, the version 1.5 was released and included an argument called schedule, but only current supported value is static. The spawn macro was powered on Silk parallel programming, and it can create a task, and the runtime schedule is responsible to decide when and where the task will be executed. So again, we have the 4 threads here and the same loop with 12 iterations, but this time we ended up with an empty thread. This thread didn't get any task. 2 threads got 5 tasks completely out of order, and thread 3 received only 2 tasks. Julia documentation lately remarked that its schedule is non-deterministic and should be relied on. However, it can be easier to parallelize recursive algorithms like the Fibonacci one here as an example, because we can just simply static scheduling may result in load imbalance if the computation of the iteration is uneven. Dynamic scheduling, on the other hand, tries to overcome this by performing the assignment according to the execution time of the iterations. It can, however, incur in overhead during the loop computation. So, since we are analyzing the loop scheduling, or how the iterations are distributed among the threads, we studied two ways of parallelizing a loop, each one using a different multithreading macro. Here we have examples of parallel loops implemented. The one with threads is the simplest and straightforward. You have the loop you want to parallelize, and all you have to do is add the macro in front of it. The spawn implementation looks a bit weird, but it produced a dynamic schedule as desired. The way it works incorporates some aspects of Silk, where each thread has a work queue, and every time a task is spawned, it is pushed to the queue. When one thread runs out of work, it steals from other threads' queues. To assure this behavior, we run these pieces of code 1,000 times in a multi-core processor with 8 threads. The macro threads produce the same scheduling for every execution, whereas the spawn produces a random assignment on each execution. Here we start talking about experimental results. The executions were performed on an Intel i5 8th generation with 4 cores and hyperthreading enabled, 8 GB RAM, and the Julia non-threads environment variable set to 8. Each experiment was executed 50 times and represent the mean value of these 50 executions. To measure the execution time, we use Julia macro time D, and with the execution time of each thread, we could calculate the load imbalance percentage. As in this formula here, the Lmax represents the maximum execution time in a thread, while the lowest L here, it represents the mean value of the execution times of every thread. We make this division and subtract 1. So here we have the percentage. To evaluate the performance of the loop scheduling types, we use synthetic kernels, which can provide more control of the behavior of the code, and also real-world benchmarks. The synthetic kernels were implemented with a nested loop. The outer loop defines the number of tasks to be created, while the inner loop defines the amount of work of the task. We have the balanced kernel, where every task has the same amount of work, and the unbalanced kernel, where the amount of work depends on the task ID. The real-world applications were selected from the benchmark suite Routinea. There's already a Routinea package in Julia. We adapted a few benchmarks to the multithreaded for this work, and we plan on adapting the rest of the benchmarks to contribute to the community later. This work, it can be found in the paper. We have a link to our GitHub where you can find the Routinea code that we implemented. The Routinea benchmarks that we chose were the SRED v2, the Speckle reduced anisotropic diffusion, and it is a method for removing noise in ultrasonic radar imaging. We also have LUD, the LU decomposition, by using upper and lower triangular products of a matrix, and BFS, breadth first search graph traversal algorithm. We divided the input of all benchmarks into small, medium, and large to compare the results. Here we have the synthetic application results. On the balanced kernel, we can see that both macros, threads, and spawn produces similar load balancing results. Since the application is regular and the iterations are identical, they were able to perform a good distribution. On smaller inputs, the time to create tasks can influence the execution time of each thread. On large inputs, the amount of tasks is huge, and it turns the difference between the iterations computation negligible. Both maps also showed similar results for execution time, varying as the input increases. On the unbalanced kernel, we can see that spawn outperforms threads both on load imbalance and execution time. When using threads, the first thread receives the first iteration, which contains most of the work, hence producing more load imbalance when compared to the other threads. The spawn macro had better execution time according to its better load imbalance. And about the real-world applications. On S-thread, we have two sequential loops, where the iterations have same amount of work. For small inputs, there is no time for the work stealing on the macro spawn. Therefore, the load balance is high. We even spotted some threads with no tasks assigned. As the size of the input increases, the load balance when using spawn is less than using threads. Regarding the execution time, the difference between both macros is small, and this could be due to the overhead generated from work stealing. On LED, we have two parallel loops inside an outer loop. As the iteration of the outer loop increases, the work in the inner loops is reduced, making the effect of the work stealing reduced as well. It was also observed that because of the non-deterministic behavior of the spawn macro, some threads remained without any task. We can see in the plot how this affected the load imbalance. The spawn had a higher load imbalance and execution time. BFS was the one that produced the most extreme results when increasing the input. The implemented code consisted of only one parallel loop that traverses all the nodes in the graph, but the amount of work each iteration held might be different. You can see that spawn was worsened in load imbalance and execution time. In fact, for large input, which corresponded to 1 million nodes, the execution time it took was enormous. This could be due to the fact that the nodes aren't contiguous in memory, resulting in high cache miss rate. Having compared all previous results, we could reach the conclusion that there is no best solution for all cases. We could see the static scheduling performing well for balanced applications, while the dynamic scheduling handled unbalanced ones better. However, the overhead from work stealing was significant, and it can worsen the memory locatedly for both the stealing and the stolen thread. It was also noticed that when the input was too small, this overhead could generate cases in which a thread would not only receive a task at all. As mentioned before, by the time this work was finished, Julia version 1.5 was released, including the schedule argument for the macro threads. Even though only the static configuration is available now, it is likely to change in the future. We are done with our presentation. Thank you for watching, and we'll be gladly answering your doubts.
Thank you, Diana. We have time for questions.
Okay.
We have time for questions. Someone has a question?
Can I ask a question?
Okay.
Sure.
Diana, that was a very good presentation. I liked Julia. I like the language, but I think I know that your work is just comparing Julia with Julia, because you are just comparing, the language. But Julia, for some tasks can be very inefficient compared to other languages. So my question to you is, in which way Julia would be different and would be better than other languages to do the same kind of things that you are doing, like LUG and these other benchmarks that you have there?
The thing with Julia, it's actually about the balance, because they actually mentioned this a lot, like the problem where you need performance, but you also waste time, because it would mean like you need to choose language like C++ and have more effort to make those algorithms. So you're right. Sometimes Julia is worse than some language. Sometimes it is actually, you can actually compare it with C, but it is also more efficient than language like Python. This is noticed. So you have to pick, like, you need to see if you want this balance, if it's important for you. Because the syntax of Julia, it is actually like really great for this. Like, it's really, really efficient and simple to read and write as well.
Yeah, I like to see that you like the language. I mean, Julia has lots of nice characters. I think it's a nice language. I just think that people need to work more on the efficient part, even for the sequential. I mean, you are talking about the parallelization, right? But even sequential performance needs to be improved. Very nice work. Very nice work, Gianna. Thank you.
Thank you.
More questions? I have a question, Gianna. Did you compare your results with C and OpenMP with different scheduling clauses?
Not yet. This is something we are planning to do.
Okay, thank you. More questions?
Yes, I have a question. So thank you very much for the nice presentation. I don't know. I don't know if you covered this, but this is just because I'm curious. And you had like at one slide mentioning the number of threads, like 8, and these were hyper threads basically. I was working in the last few months with hyper threads, and it turned out that in most cases, when it comes to scientific computing, it is better to turn off the hyper threading. So you're really using the logical cores, not the physical cores, I mean, sorry. And this was better for the performance. This was only for pthreads, OpenMP or whatever. Do you have some information on how Julia works on that and what the performance is when you turn off the hyperthreading?
No, I don't really know about this.
Well, I was just curious, maybe you know it, because I mean, the
it
other
is
thing
good that you mention it, because it could be something to be looked for.
Yeah, especially when you use SIMD instruction sets. There you have on the physical cores, you have the vector registers, and these vector registers, if you have hyperthreading on, the threads interfere, or they will fight for the resources, and this could mess up your performance. I was just curious about that. I mean, if maybe you had some information.
Yeah, no, I haven't tried it.
All right.
Thank you, Diana, for the nice presentation. Let's go to the next paper. The title is FFT Optimizations and Performance Assessment, Target Towards Satellite and Airborne Radar Processing. Maron Schlemon, you are here?
Yes, I am. I just asked the question.
Okay. Could you share your
live stream or live presentation?
No, please live stream.
Yeah. Okay.
Hello, everyone. Thank you very much for attending this presentation. My name is Maron Schlemon, and I work as a PhD candidate at the Microwaves and Radio Institute of the German Aerospace Center in Pfaffenhofen, Germany. And today I'm going to present you my work on FFT optimizations for satellite and airborne image processing. For this presentation, I have the following agenda. First, I will explain why efficient algorithms are needed in the field of radar image processing and which role the FFT plays. Next, I will discuss the optimizations that were implemented in order to develop a high-performance FFT using the Radix4 algorithm. I will show the performance of the proposed FFT and compare it to FFTW. Finally, I will give a short conclusion and briefly discuss our future work. The topic of my PhD is real-time synthetic aperture radar. You can see a very simple example here. As shown, during the data acquisition step, the aircraft is flying through a specific scene and recording the data of the pre-transmitted signal or pulse. This data represents the input of my work and has to be processed or focused. On the left-hand side, you can see the data after the acquisition step. Our goal is to process the data in order to get a focused image, as shown on the right-hand side. This requires a lot of processing steps, and my task is to write a high-performance library that contains efficient functions in order to reduce the computation effort. The library is written in C and uses a lot of single instruction, multiple data techniques, as well as pthreads. Two major steps are the range compression and the azimut compression. Their performance depends heavily on the FFT function. I explain the range compression on the next slide. For debugging, I have developed a Python interface which allows me to use all the C implementations. The range compression contains a real-to-complex FFT, a multiplication by a reference function, and an inverse complex-to-complex FFT. The result is range compressed data in time domain, which represents a step of the processing chain, which I explained a slide before. I want to show now how the real-to-complex FFT is implemented. The data is stored in raw major order. Since we are using Intel simple instruction sets, the data has to be aligned, either 32 bytes or 64 bytes aligned, depending on the technology. The Radix4 algorithm requires the dimension of the samples to be power of 4. The dimension of the lines can be any number. Now the question is, how do we execute the FFT? You can see here the FFT kernel, which is based on 1D FFTs. It takes a specific plan as an input parameter, and now each row of the data is loaded into the kernel. And then the FFT is executed and the result is stored into a new memory location. In a similar way, the multiplication by a reference function is executed. Again, each row of the data is loaded into the multiplier kernel, which takes a reference function as input. The output is stored back into the input array. So this time it is an in-place method. I have shown that the processing time of the compression algorithms heavily rely on the FFT performance. In order to achieve real-time capability, a highly efficient FFT is required. There are many open source FFT solutions and libraries on the internet, but we decided to have our own implementation in our library. After testing many FFT algorithms, we decided to use the Radix4 algorithm, which gave us the best performance. The complex valued Radix4 algorithm, or Radix4 butterfly, is given here. A, B, C, and D are n-quartered point DFTs, and the trivial factors are represented by W. In the following slides, I want to discuss the optimizations of the Radix4 algorithm. We optimize the structure of the Radix4 butterfly by first splitting the data into its real and imaginary parts in order to make vectorization easier. Second, we restructured the butterfly in order to reuse pre-calculated values. For example, the sum of A and C is required twice, and also B and D. These sums can now be reused as shown here. Thus, we can reduce the calculation effort in the real-valued butterfly by 4. The same applies to the imaginary valued butterfly. The third optimization is the pre-calculation of the twiddle factors. Restore the values in the lookup table and redeliver it whenever it is needed to the FFT kernel. The fourth optimization contains the reordering stage. The output of a radix 4 FFT is in bit reversed order. To rebuild the original order, a reordering stage is required. We pre-identify the indices of the elements that need to be swapped. For example, the first and the fourth element of an 8-point FFT need to be exchanged. Restore the index 4 in a reordering lookup table. Next, we swap element 3 and 6 and store the index 6 again in our reordering lookup table. The reordering stage is a scalar function and cannot be easily vectorized. Another optimization step is to resolve the radix 4 stages and their individual improvements such as pre-calculation of loop parameters and indices. Finally, we vectorize the algorithm using Intel SIMD instruction sets. This approach can be seen in this table for a 4K FFT. The first stages can be easily optimized using YMM registers. Step 5 and 6 require the smaller XMM registers, which leads to a decrease in performance. This impact of the breakdown to the smaller registers will be discussed later. As mentioned before, the reordering function is scalar and requires 2016 swaps for 4K FFT. I want to briefly explain our processing strategy. We first create a FFT plane that contains all the lookup tables that we just discussed. For example, the loop boundaries and parameters for each stage, the twiddle factors, and the reordering lookup table. Then we execute the FFT. The FFT kernel takes the plan as well as a split complex array as input. In order to estimate the performance of our FFT, we took the FFTW library as reference. We measure the performance by using the read time step counter instruction, which returns the number of clock cycles that our function needed to calculate the FFT. You can see here an example of how we measured the FFTW performance. On this slide, I want to go quickly through the test parameters. We tested 1D FFTs for different sizes, from a 64-point FFT to a 16K FFT. We tested single-thread versus single-thread performance. We used the following compiler flags and evaluated the better results. To have a solid evaluation, we executed the FFTs 1000 times. We tested single precision versus single precision only. We activated the SIMD version of FFTW by using the following setup in order to have a fair comparison. We used FFTW's highest performance mode, which is called FFT exhaustive, in combination with their wisdom method in order to save planning time. Finally, you can see the parameters of the test system on the right-hand side. Let's have a look on the test results. In this table, you can see the performance of our FFT, which is called VecFFT. For our 4K FFT, the median has a value of around 25,000 clock cycles. In this table, the performance of the scalar version of FFTW is shown. Comparing these two tables, we can see that our VecFFT calculates the FFT up to 4 times faster than the FFTW. Especially for smaller sizes, this difference in performance is significant. In this table, we can see the performance of the SIMD version of FFTW. Now, the FFTW library calculates the FFT up to 20% faster than our proposed VecFFT. Since we wanted to know which impact the slow, non-vectorized reordering stage has, we tested our VecFFT without reordering stage. The result is shown here. Without the reordering stage, the proposed FFT is around 10% more efficient. On this slide, we can see the results of the tests in one single plot. On the x-axis, the test sizes are displayed, and on the y-axis, the corresponding median values of the clock cycles. One can see that the reordering stage of the Vector 50 has more impact for larger sizes. This slide helps us to understand the problems of our FFT implementation. We take the 4096-point FFT as an example. We tested each stage alone and measured the clock cycles. The first 4 stages require 9,000 clock cycles together, which translates to around 2,250 cycles per stage. The breakdown to the smaller registers in stage 5, which is required because of the structure of the RX4 algorithm, is expensive, leading to an additional 1,250 clock cycles. That means that the first stages are around 35% more efficient. The last stage has a special structure. As discussed, it uses lower gather instructions in order to build the required vectors. These instructions are costly, and they cost additional 1,200 cycles compared to stage 5. Finally, we can see the extensive impact of the reordering stage. With an effort of 8,000 clock cycles, it takes nearly 30% of the total performance. It needs 5,750 clock cycles, more than the optimal case. So, our future work consists of 3 steps. First, we want to replace the smaller XMM by the bigger YMM registers in step 5 and 6 in order to increase the performance. Second, we want to eliminate the slow gather instructions of step 6. And finally, we want to spend a lot of time on optimizing the reordering stage. A brief conclusion of our work is: we have accelerated the FFT processing using an optimized Radix4 algorithm that can be compared to FFTW's SIMD version and the highest performance mode. We have shown that the first stages are well optimized. However, the last stages, as well as the reordering stage of the Radix4 algorithm, show less efficiency. Therefore, our future work will concern the optimization of these less efficient stages. This was my presentation, and thank you very much for your attention.
Thanks, Myron, for your nice presentation. You have time for questions. Myron, I have a question for you. Your main focus are airborne or airplane platforms. Do you intend also to evaluate energy consumption?
This is not for now. For now, this is not an important point, since we have an onboard system which everything there is calculated. They have a lot of norms and regulations, and I'm testing my code on this system. So whatever I do on the system is okay for them.
Okay.
Do you have any idea or on how to improve the performance of the reordering phase?
Yeah. So maybe one important note: this what you just saw was the state around 6 months ago. And since then we spent a lot of time on this reordering stage in stage 5 and 6, and we optimized it a lot. And for now, we are trying to have a patent on that. And until this is under review or ongoing, I cannot talk about this. But we spent a lot of time and we resolved the problems with the reordering stage. And now we have a lot like similar performance as FFTW, and even for some specific numbers or sizes, data sizes, we are even faster. And yeah, but this will be like maybe another paper, or let's see how what the future brings.
But this reordering was done, this is just a rough idea. You don't need to enter into details.
Yes.
Was it done through shuffling on the register, things like that, or you only work on the memory itself, memory access?
We were trying to do that. We are trying a lot. We are trying for 6 months a lot. We are trying to reshuffling. We are trying to put stage 6 and the reordering stage together. We were trying intermediate exchanges, like intermediate reordering stages. Let's say after each stage, we try to reorder and then calculate it, and then we found out there was like a benefit, of course, but the benefit was like maybe 5 or 6, 7%, but not more. So we had to really like rewrite the radix 4 algorithm, and now it's not no longer a simple radix 4 algorithm. It's just basically a new algorithm, or let's say like an updated radix 4 algorithm with a and we put like the last 3 stages together, you know, to have the better form of performance.
Well, maybe this kind of thing you have also to try to pipeline it with computation, because these are memory. So
yeah, we did it. We did also loop unrolling, for example. We tested a lot, but as I told you, the improvement was not big enough. So yeah, it's still, the point is, if you want to do it,
get more.
If you want to do it in place, and then you really have to like have some kind of a buffer, and then you have to store like the value you want to swap in the buffer, and then to take it back, and all these micro operations were like destroying all the performance. And but we did, as I told you, like a lot, and then for now, like we only have a vectorized version. There's no Muscala operation in the newest version, and this allows us to improve the performance from like really a lot.
Okay, interesting.
Okay, I have another question here for Christian. Did you consider another level of parallelization for the FFT rather than the vectorization, like taking advantage of the other cores of the CPU to improve its performance?
Can you repeat the last sentence?
Like taking advantage of the other cores of the CPU to improve its performance.
Yeah, exactly. But we had the following plan. We wanted to have the best single thread performance, and based on the single threads, we are building our P threads, for example. I showed you in the beginning a 2D matrix, and we are using the P thread like this. So we are splitting the big matrix in let's say 4 subsamples, and we are putting like a thread on each of these samples, like subsamples, because we have on board only like small CPUs, like old CPUs, and they most of the time they only have 2 or 4 cores, so we are limited with the threads. And this is why I asked my question to Diana. Like we there have only like the physical cores. We tried it to extend the number of threads by activating the hyperthreading, but we noticed that the threads were concurring between each other, and then we lost a lot of performance. So we turned it back off, and then for now we only have 4 threads, basically, or 4 cores. On these 4 cores, we are optimizing the FFT by splitting the input data into a specific, like into reasonable samples, and then these samples we are putting on the threads, and then we have for now the best result. This is far away from being real time, because we are really limited with the memory, with the in general the memory. Yes, when it's also with the RAM, we are very limited, so we cannot do whatever we want in space. It's very, very tough. And yeah, this is for now the state.
Okay, thanks again, Maron, for your presentation. Let's go to the last paper of Wamca. It will be presented by Daniel Domenico. The title of this paper is Jumpy, a C++ parallel programming interface allowing the implementation of custom and generic scheduling mechanisms. Please, Daniel, would you do this thing for us?
Hi, Clicia. Here is Gerson. We have a video to play.
Yes,
I play myself. You can play.
I asked the guy in code to.
Okay, I will play the video.
Okay, play your video. Okay.
Thank you.
Hello, I am Daniel, and I'm going to present our work, JMP, a C++ parallel programming interface allowing the implementation of custom and generic scheduling mechanisms. This paper was developed by me and Professor Gerson Cavalheiro. Our presentation is divided in 6 parts: context, objectives of the paper, related work, JMP, that is the interface, programming interface that we are proposing, preliminary results, and to finalize, conclusion and future works. So, new initiatives in parallel programming models are continuing being developed in order to address some challenges, like access to shared data, synchronization of tasks, and load balancing. And we have also the N versus M interfaces, like OpenMP, TBB, and SIL. This kind of interfaces are modeled following this schema, where we have a scheduler that schedules some tasks represented by N and that are defined explicit in the application code. And they are scheduled then to the threads that are represented by M and that are available in the system. So, the objective of our paper is proposing JMP, that is a high-level C++ parallel programming interface that follows the N versus M model, and it provides a full dissociation of its programming interface from its scheduling mechanism. And with JMP, it's possible to implement a customized heuristic to be applied at runtime. And we also aim with JMP to support multi-core and heterogeneous devices, being these heterogeneous devices a future resource. So as related work, we have the C++ parallel programming interfaces. We have divided them in 2 categories. First, the standard ones, OpenMP, Silk, and TBB, that are commonly provided by the hardware vendors of parallel hardware. And the new initiatives like HPX, Cocos, HPSM, and others. And considering scheduling, these tools offers some predefined options to schedule an application, and some of them allow custom schedulers, but to implement it, it's offered an interface associated with the programming. Is the same interface. When you program your application, you have to program the scheduler. So, with JMP, that is our C++ parallel API, we offer full dissociation of its programming interface from its scheduling mechanism. And we can provide scheduling manipulation at runtime through a generic and customizable scheduler. JMP also provides multi-core parallelism and a parallel loop pattern. Also, JMP have a clear separation of the concepts from a parallel application. That are 3: task, thread, and scheduler. The tasks is used to define the application concurrence. The thread is used to map processing resources to compute these tasks. And the scheduler that coordinates interactions between tasks and threads. That is, it schedules at each launched task to an available thread in the system. Here we have the Jump class diagram, when we have these three concepts from a parallel application represented as classes. Here in the right side, we have the task represented, and it is used to map the parallel code. In our model, we use a callable class to map the parallel code. This parallel code must be a C++ object like a functor, a lambda, or even a class method. So then this parallel code, it is encapsulated in the task, so it can be called during the application execution. And using metaprogramming, we provide type safety of parameters for this parallel code. Here in the left side, we have the thread class that is used to map the processing units of this system, and this is done extending this class in the application code. So, and this approach can be used in the future to add support to heterogeneous architectures like GPUs to our interface. And to finalize, we have the scheduler that has a scheduling algorithm inside it, used by it to provide a custom heuristic. Then this class schedule algorithm can be extended and to implement this custom heuristic, and with that we have a dynamic scheduler and totally separated from the task code that was mapped in the task class by a callable. Here a code example to illustrate how jumps works, and we use a Fibonacci recursive application. So first we have to include the jump libs to access jump constructs and functions. So here we have the declaring of a task using templates to provide type safety, and the scheduler, the scheduling policy, when we have as templates a schedule that is our custom heuristic, and the thread when we map the processing resources. These both classes will be detailed in the next slides. So here in the Fibonacci code, we create the both tasks, left and right. And then we spawn that then using the scheduling policy. So for the left task, we add a node value as third parameter, and for the right task, we use an even value. Then it will be clarified. This will be clarified when we show the scheduling algorithm. So after spawn, we sync the tasks to finalize the computation of the Fibonacci. Here we have the scheduling algorithm when we can implement our customized heuristic. So we extend the schedule algorithm class from jump, and we have two services, create thread and execute. So we use the context that is a parameter received by these services to implement the heuristic. So if it is a not context is a not value, then a new thread is created and returned. Otherwise, it returns a null pointer. And here in execute, if the context is odd, then the task is executed by the last thread created, else it is executed in the current thread. Remember that we passed when we spawned as third parameter odd and even, so the right task will be always executed on the current thread because it uses as context an even value. Here an example of the thread class that was extended to map a computational resource to compute the text. So here we used thread implementation from C++ to create and to join to synchronize the tasks that are being executed by a thread. As preliminary results, we used two applications implemented with JMP: Anybody simulation and matrix multiplication in a platform with 20 cores. The first experiment was an overhead. Gauge the overhead of JMP. Then we executed the applications implemented with JMP using a single core and divided this time by the sequential time of the application. And here we can see that JMP did not add any performance penalty to the benchmarks because the value of this division is lower than 1. That means that the JMP version executed a little bit faster than the sequential time. And we also gauged the performance from the applications. And here we can see that the Anybody application scales well with more CPUs available to execute it, even when we changed the block size. The same scenario was achieved with matrix multiplication benchmark when we implemented it using parallel form pattern. So, to conclude, we implemented and presented JMP, a C++ API that provides a full disassociation of its programming interface from its scheduling mechanism. So, with JMP you can implement a customized heuristic to be applied at runtime by the scheduler. Some preliminary results showed that JMP did not add performance penalty or overhead over sequential time of the applications we tested, and the applications scaled for all CPU configurations. As future works, we intend to add new parallel patterns to JMP, like parallel reduce. We also want to execute advanced experiments using the generic scheduling mechanism and add support to heterogeneous architecture like GPUs, and this will be implemented as we showed before using the generic scheduling mechanism. So I'd like to thank you all for the attention.
Thanks, Daniel. We have time for a few questions. Someone has a question?
I have one. You did this interface to provide custom scheduling, but did you implemented any custom scheduling mechanisms?
Hi, I'm here, Gerson.
Oi, Gerson.
This work is an insight. In fact, you believe that applications have regular portions in program that you need to change the scheduling strategy. And also, in heterogeneous architecture, it seems obvious that different scheduling must be applied. Nowadays, you have only preliminary results with toys experiments, change algorithms, scheduling different kind of loops. Only that for now.
Okay.
Okay. More questions?
I was just wondering if you have to consider GPU, so you have to mix different kind of code, because the code that is going to GPU will be different to code that will go into CPU, things like that. Is it easy to
Yes, yes. If you have enough people to work, maybe a path to walk on, but currently you are just make experiments trying to explore all facilities of C++ before to enter this new adventure in heterogeneous architectures.
Yeah, it will be complex. Although you use something like Opencl, but okay, that's nice.
Okay. I have a last question, Gerson. Do you think about use hyperthreading? Do you know if the results you have the same behavior?
No, it's very difficult to deal with the hyperthreading. We don't treat exactly this problem at this moment. There's many features involving very low level programming, like in cache, but it's an important point because we are focusing in scheduling different patterns of loops, reduce, scan, then it's relevant, but it's necessary to take into account the architecture characteristic, and it's very low level, for instance.
Okay, thank you for your presentation. Claude, you have the words now.
Okay, thank you everyone. As I said at the beginning, thank you all of you for doing your best to have Wamca remain alive and increasing in the interest of all the HPC community. Thank you also to have included Wamca in your agenda of today. So we are all concentrated, nice talks, nice interactions. And I hope we will still have this community active, increasing. So have a nice day, end of day, and it was very nice. So I'm going to send a message to all people that presented something to Wamca. If you want to provide me your slides, then I will put it on the web. So I will send you a message and the link for your video too. So the web page will contain all the material so that people can access it also. Thank you, all of you, and have a nice end of the day. Thank to everyone. And we are very happy of this edition of Wamca.
Yeah, okay.
And thank you, Claude, for keeping this spark alive of Wamca. Thank you very much for your hard work this year.
Pleasure.
Congratulations for the organization.
Yeah.
Thank you, thank you.
Thank you all for the collaboration.
Yeah, with pleasure, yes. It's very good collaboration, fruitful.
We will see tomorrow on this back.
Yeah.
Yes. See you tomorrow. Bye
Thank
bye.
you, everybody. Bye bye, Claude. Thank you,
Bye.
everybody. Bye bye.
Bye bye.
Bye bye.